This is part 2 of lecture 6 of Logika računalništvu. In the first part, we looked at the bounded satisfiability problem in predicate logic and how it could be reduced to the ordinary satisfiability problem in propositional logic. So if we have a bounded satisfiability question in predicate logic, we can translate it to one to a SAT problem in propositional logic and submit it to a SAT solver. Or what we can do is directly use a tool that does that for us and works with predicate logic itself. So that's what we're going to begin by looking at. We're going to look at a computer application called the Alloy Analyzer. So let me write that. The Alloy Analyzer, because it analyzes predicate logic axiomatizations and of theories and their models. So analyzer. And it's quite an old piece of software. It's also mentioned or discussed quite a lot in the textbook, the Huth and Ryan textbook. Let me open the software. So here we are. Here we have the Alloy Analyzer. It's implemented in Java. This is version 5. It's implemented in Java. This is from last year. So it's a modern version of the Alloy Analyzer. It uses a Java SAT solver called SAT4J. It's not the fastest SAT solver around, but it's anyway good enough for the applications we're going to do. So here we're going to get, in this little part of the window, we're going to get the analysis of what we ask the analyzer to do. And here we're going to write our theory, and it would take a long time to do it from hand. So let me load the theory that's prepared for the lecture. So I want to open from desktop the lecture theory, and here we are. And here we basically have axiomatization together with the commands we want the analyzer to execute. So those are going to be the queries that we're interested in exploring properties of the axioms. So the green lines here are comments, so that we know understand what's going on, and the blue and black, the blue are keywords, but the blue and black are the axioms. And you might notice immediately that these axioms do not look very much like axioms in predicate logic. It looks much more like a program. So I think one of the design considerations of the analyzer was that the idea is people are going to use this to analyze software and computer systems, and the people that do that are going to be much more familiar with programming than with predicate logic. So although these are really stating axioms in something called multi-sorted predicate logic, actually a slight extension of it, as we'll see later, of predicate logic, but essentially these are predicate logic axioms. The way the syntax has been constructed has been designed to be sympathetic to someone who's more experienced with programming than logic. So I'm going to go through the axioms in turn and then explain them, write them down on the notepad in predicate logic form. So here we're saying we're giving ourselves in the signature a class of FS objects. We can think of that as a unary predicate on the universe, although in this case everything we deal with is going to be an FS object. So we're just going to think of this as just referring to the universe of everything we have as an FS object. So we're not going to really put this in our axiomatization. FS object stands for file system object, and what we're going to axiomatize is the structure of a file system as one would find on a personal computer, or in the kind of file systems that most operating systems have. So those are file systems in which we have directories or folders, as people often call them nowadays, but and one has files, and the idea is a directory, or equivalently a folder, contains a collection of things, and that collection of things are either individual files, or they are themselves directories. And this is saying every element of the file system has a parent directory, in fact has at most one parent directory that contains it. So here the notation is we have a kind of parent function that will give us that lone means at most one. So the parent function applied to a file system object will give us at most one directory. So not every element of the file system will have a parent directory, as we shall see. So let's go to the notes. I'm going to write down the example. I may not write out every single one, but I'm going to show how one can translate this into predicate logic. It's essentially a predicate logic statement. So this is we have a so there's the parent function, but the function is not a total function, so we don't want to have a function symbol for it. We're not saying that every element of the file system has exactly one parent. So the best way to represent that in predicate logic is as a predicate symbol of arity 2. So we have a predicate parent of arity 2, and every element, every file system object, so let's just call it every object, has at most one parent. So here we've extended the signature, we've added something to the signature, and the axiom we put in is for all x, y, and z, if the parent of x is y and the parent of x is z, then y equals z. Okay. That's just the first line so far. Then we're extending the signature with something called, with a set of directories. Every directory, it extends fs object. It's a bit like in object-oriented programming languages, but this is saying it's a subset of the set of fs objects. So directories are particular fs objects, and there's a contents operation that acts on directories, and the contents of a directory are a set of fs objects. So we can write that in predicate logic as follows, that we have a predicate directory that has arity 1, because we're just saying when an object is a directory, and a predicate contents. So we've got two predicates, directory of arity 1 and contents of arity 2. And contents is something that applies to directories. We're only interested in the contents of directories, not of files in this sense. This means what the directory contains. So only directories have contents in this sense of contents. And so that's saying for all x, y, contents. So if x has contents y, then x is a directory. Whoops. This should be for directory. Okay, go back to the analyzer. So we're also going to have another set of things called files. And there's no axioms at all about files, so we're just adding that to the signature. So far, no axioms about files. We've got a predicate file, varity 1. Also, we're going to have something called a root. So there's going to be, so here we're adding to the signature a root, and this is again a set of things. And this time roots are all directories, but roots have the property that there's exactly one of them, and the root has no parents. So this is why we needed to require that not everything has a parent, because we're going to have a root directory in the file system. So there's quite a lot in this axiom. Notice it's written in a rather succinct way, that we have exactly one root, that roots extend directories, and that roots have no parents. So to write that out fully in predicate logic takes a bit of time. So let's actually just carry on. We've got a predicate, also root, and there's exactly one root. So there exists an x such that x is the root. For all x and y, if we've got root x and root y, then x equals y. The root has no parents, so for all x, it's not true that there exists a y such that the parent of x is y. So we've got exactly one root, and it has a parent. Is there something I've missed? Let's have a look. Let's get back to the end. So we've got one root. Yes, every root is a directory as well. So I missed that. So let's put that on here. So for all x, so the root is a directory. Well, the only root, the unique root, is a directory. So for all x, root x implies directory x. So now all file systems are either files or directories. So there's a neat way of saying that in the language of Alloy. So all this was, although we've been writing them as axioms in predicate logic, it's considered as just simply specifying the signature in Alloy. The signature allows us to state properties of things as we declare it. And now we're asserting what Alloy considers as axioms, and they're going to also be axioms for us. So this is a succinct way of saying that every object is either a file or a directory, but the plus symbol means and it's not simultaneously a file and a directory. So it's exactly one of a file or a directory. So again, we need two axioms in predicate logic to express this. So we've now got, we're not extending the signature anymore. We've got for all x, file x or directory x, and for all x, it's either the case that x is not a file or x is not a directory. So it can't be both. And now a slightly subtle point, which is that if we've got a directory and we look at the contents of the directory, then the parent of the contents is the directory we've got. Okay, so that means that an element in a directory, that's the contents of a directory, cannot be the contents of two different directories, essentially. So we can say that as for all x, y, z, contents x, y. This already implies that that x is a directory, I think. Yes, from this. Contents xy and parent yz implies that x equals z. Okay, so all these are very intuitive properties of file systems. And now we can try to see if our axioms are consistent. I mean, it's very obvious that they are consistent because the file systems we have in mind from the file systems we actually have on computers pretty much satisfy these axioms anyway. But anyway, we can use Alloy to explore, to see what the models of our current axiomatization look like, because perhaps we've also missed some axioms that we might need to properly axiomatize a file system. So now I'm going to use the run command to try and find a model of the axioms we've got so far. And because it's a bounded satisfiability checker, I'm bounding the size of the model at 6. And the way that we ask is there a model of the axioms, is we run a test predicate over the axioms. So the test predicate is we look for a model satisfying a particular predicate. And the test predicate we're going to have this time, which I call isModel, simply requires that the number of directories and the number of files are both strictly greater than 2. So we need to have, so I'm asking, is there a model of size at most 6 that has at least 3 directories and at least 3 files? So of course, if it's going to have 3 directories and files, and since a directory cannot be a file, we had that as an axiom here, then it's going to have exactly 6 elements. But anyway, if such a structure exists, so can we actually satisfy these axioms and find a structure with 6 elements in it, 3 directories and 3 files? So to do that, we say execute. And it's telling us that it's running is model for 6, so it's running the query, and it gives us some statistics about how it translated this to a problem for a SAT solver, and it reduced it to a problem with 838 Boolean variables. Doesn't matter about the primary variables, but 838 Boolean variables and 1,526 clauses, and it found a solution in 183 milliseconds, and it's found us an instance. So one of the nice things about this kind of tool is that we can click on instance and have a look at a visualization of the model. So if we do that, then here we have our, so we see here we have the model that's been found. So we've got the root here, which is of course a directory, the 2 other directories, and 3 files. So we have 3 directories and 3 files. The parent relation between a directory and its contents is so root is the parent of directory 0. This is the contents of directory 0. Directory 1 is the parent of file 2, but there's no contents relation in the other direction. So that's not too good. We would like to have a contents relation in the other direction. So we're missing an axiom about that. And also here we've got a loop that directory 1 is a parent to itself. And also we have that although we've got the root directory, we can't reach other directories by going down through the directory structure from the root directory. So the point is this does not look much like we would like a file system to look. So we've got some axioms missing here. We could try and look at some more models. Okay, so it's pretty similar, but again we've got a directory that this time is its own contents. We don't want that sort of thing. Yes, and here we've got some more loops. So we've got some axioms missing. So what sort of axioms might we want to add? Well, one natural one is to say that every element of the file system is accessible by a sequence of contents relation from the root. So it may take a while to get to it. You might have in general you have a tree structure to your directories in a file system. The root is the root of the tree, and you might need to go down through a directory and several subdirectories to get to a particular file, but nonetheless there should be a path from the root. And in Alloy we have a nice way of stating that axiom, so we can add as a fact. So every file system object is in the set that we get by this star here, means following an arbitrary number of contents relations from the root, including 0. So the root itself will be there because you don't need to follow the contents relation at all, but every element of the file system should be obtained by applying the contents relation to the root some finite number of times, possibly 0, but at least a finite number of times. Okay, so how would we write this in predicate logic? So let's go to here. So we might say this as every x is reachable from the root using the contents relation. Let's say reachable from the root using the contents relation. Reachable here means by applying the contents relation some number of times, possibly 0. So we can say that, and one way of saying it is for all x, there exists a y such that root y, in fact it's unique, the root, we've got an axiom saying that, and now we want to say y is reachable by an arbitrary number of applications of the contents relation. And to do that, I'm going to actually do something that I can't really do in predicate logic. I'm going to write content star x, y. And this is again notation for reachable from x, for y is reachable from x along the contents relation. And I'm just going to say here, for later reference, let's put it down here. Content star is the transitive reflexive closure, so nice mathematical terminology for this reachability idea. Transitive reflexive closure of the contents relation. See you later. And just to give you a little hint about what's coming later, is that later we're going to see that we can't actually express this in predicate logic. So alloy actually goes a little bit beyond predicate logic in its expressive power, because it does allow us to formulate this transitive reflexive closure. So let's go back to alloy. And now I've added this fact, and let's save that and then execute again. And now an instance is found, and now it looks a little bit more like we would expect. Here we've got one root and the other two directories. So it's a flat directory. The root, the only directory that has contents. The other two directories are empty, and the files and the files are also in the same root directory. Actually, one thing I want to do is notice now that all the parents and contents relations are working properly. So we now, when we have contents, we also have the parent relation and vice versa. So that seems to magically follow from this axiom we've got. And because of that, it's a bit annoying to see both of them, because we're getting all these duplicated lines. So I'm going to hide the parent relation. It doesn't matter which one we hide. So let me click on oh no, I don't want to do that. I'm just trying to remember. I think theme's the right thing. Okay, good. It didn't seem to work when I was first hovering there. Right, so I want to hide the parent relation, I said. So I click on parent, and these are the defaults for how to draw it. So we've got show as arcs. I'm just going to turn that off and apply it. And now we've got the contents relation. It's also nicely turned the tree up so that it's upside down, so it's growing down. And this looks like the kind of file system we want to see. Let's close that, and then we can start exploring. We can look for more models. So once you've looked at one model, we're still running the same query, looking for a model with 3 files and 3 directories. But we can look for as many models as we want. So if we ask for the next one, then it does another search, or it continues the same search and gives us another one. So we've got a more interesting directory structure here. So we've got a root, the directories are in a line like this, and the other two files are at the bottom. Let's just look at one more. Okay, and yet another structure of it. Okay, so basically we get a way of visualizing the consequences of our axioms, and we saw that our original set of axioms was not sufficient to implement the idea that every element of the file system is reachable from the root. So we added an axiom to do that using this star, this transitive reflexive closure. And so let's now try and convince ourselves that this axiom is somehow the correct one. So let's try and check some properties that we would like to see that hold in our file system. So to do this, I'm going to comment out the running testing for a model of size 6, because when you run the analyzer, it only answers the first query that you've got. So I was asking, is there a model of size 6? It's answered that. So here's our new axiom. That's fine, that everything is reachable from the root. And now what I want to do is I want to check. So a good property of a tree structure of a file system is that it's acyclic. We don't want any loops of directories so like we had in the first examples before we put the reachability axiom in. We had axioms in which the contents and the parents relationships were going round in circles, and we would want to avoid that in a real world file system. So we'd like it to be a nice tree with no loops, necessarily with no loops in it. So we can state that as the acyclicity property. And the acyclicity property is that there are no directories that are in their own hereditary contents. So the hereditary contents here is again some modification of the contents relation, and it's again reachable under the contents relation, only this time by a path of length at least 1. So we're saying no directory is reachable from itself along the contents relation by a path of length at least 1. Every directory is trivially reachable by itself using a path of length 0. So we can't use the star here because then this would simply not hold, because every directory is reachable by a path of length 0. But we want to see that we want to see, are there models in which so here I'm asserting a fact that we want to check. So I'd like to state this as a property that follows from the axioms. So I'm asserting we believe it is the case from the axioms that there are none of these loops in the file system under the contents relation. Now, as I said in the first part of the lecture, we can't actually check that properly, that it really is a logical consequence. To do that, we would need to prove that this follows from the other axioms. But we can check that there are no small counter models. So let's check the assertion for, that said 8, but I need to get my virtual keyboard here. Oh, no, not 110. That'll take us a very long time. Let's check it for 10. So what we're doing here, we're stating a property that we believe holds, that we believe is a consequence of our axioms, and we're going to check that up to bound size 10. So check that this property holds for all models of size less than or equal to 10. So let's execute that. So it's taking a bit of time to solve. Maybe I shouldn't have changed 8 to 10. Well, let's leave that running, and I shall continue in the lecture. It's going to tell us how long it takes us to solve it, if it does solve it. Otherwise, we'll come back and interrupt and go back to 8. But let me tell you that it is a consequence of the previous axioms that the file system is acyclic. So hopefully this model checker will be able to tell us that. You see that it's not super efficient. 8 it would have answered immediately. 10 it's having some struggle with, but we shall see whether it will solve it. So let's come back to that. That's it's going to be interesting. So let's have a new page here. So the alloy example uses the transitive reflexive closure This is in the reachability axiom. Oh, it's going very slowly because alloy is running in the background. Well, we shall see. So it uses the transitive reflexive closure in the reachability axiom and the transitive closure I may have to abort my process if we'll see. And the transitive closure in the acyclicity property of the contents relation. So in general, for a binary relation R, for a binary relation R, the transitive closure is normally called R plus, but in alloy it was called R hat. Is defined by, so the point is that X is in the transitive closure, X and Y are in the, so I'm going to write it like this. So I'm writing R plus as an infix relation, so this is saying R plus of the pair X comma Y, but let's write it infix. So X and Y are related in the transitive closure. This holds if and only if, let's just write it informally, so either X is related to Y, or there exists a Z1 such that X is related to Z1 and Z1 is related to Y, or there exists Z1, Z2 such that X is related to Z1 and Z1 is related to Z2 and Z2 is related to Y, or and so on. And the point is, this is an infinite disjunction. Well, this is a point, infinite disjunction. So what it's saying is that x and y are related in the transitive closure if there is a path of some finite number of steps, not zero, that takes us along the R relation which takes us from x to y. So either y is reachable in one step or it's reachable in two steps. So if it's reachable in two steps, we need to have an intermediate state to go into, that's Z1, or it's reachable in three steps, so then we need two intermediate states, or it's reachable in four states, and so on. So that's the transitive closure and the transitive reflexive closure. Oops, I want to be in black. Is defined by x and y are related in the transitive reflexive closure if and only if, well, they're either related in the transitive closure, so either y is reachable from x by a path of at least one step, or is reachable in zero steps, in which case that means x equals y. Okay. So it's clear what these relations mean, and in alloy we have the star operation to apply to a relation, and also the plus operation with this other notation here, but still we can apply the, if we've got a relation, we can ask about the transitive closure of the relation and the transitive reflexive closure of the relation. So what I want to end today is by showing actually transitive closure and transitive reflexive closure are not definable in predicate logic, in first order logic. So actually the language of alloy gives us a language for axiomatizing properties. As we've seen, it actually goes beyond predicate logic. But nonetheless, it's still amenable to reduction to SAT solving. So nonetheless, the bounded satisfiability, because this is what alloy does. Is reducible for the language of alloy is still reducible to SAT solving. Still reducible Now, I'm not going to tell you how that's done, but the point is this: the idea of reducing bounded satisfiability to sat solving is very powerful, and so can also be used for more expressive logics than predicate logic. And alloy is already giving us a more expressive logic than predicate logic, and that's useful because, as we saw, it's rather a useful property to assert of a file system that every state is reachable from that every element is reachable from the root directory. Okay, let's just go back to alloy to see if it's answered our query yet. Oh, unfortunately it hasn't. So let's stop it. So solving stopped. Well, I could go down to 9, but I don't know. I had 8 in there for a good reason. So let's insert 8. And save that, and let's ask whether or not the acyclicity property is true for all models of size less than or equal to 8. So I'm going to execute that. Oh, well, here it goes. It's still taking a bit of time. Okay, well, let's go back to the lecture. Oh, no, we've finished. Excellent. So no countable has been found. Sorry, not no countable. No counterexample has been found to the acyclic assertion. So if there is a counterexample, the model has to have at least 9 elements in it, 9 file system objects in it. So it gives us, as explained in the first part, it gives us cause to hope that the acyclicity property might be true, might be a consequence from the axiom, and indeed it can be shown that it is a mathematical consequence of the axioms. But in general, one would like the computer to do the work, as I said last time, so it's nice to be able to explore, use alloy to explore to see whether or not it looks like this property is likely to be true. So here we're sort of trying to check to see whether this condition is likely to be valid. It may be valid. That's true in all the models of the axioms, because we have cause for hope here. So that's one of the applications we have of using an analyzer like alloy. The other application was testing the axioms by looking at different models of them, as we did at first, and then finding out that we'd missed out some property, or you might also find out that you've axiomatized some property incorrectly, or you might need to rethink. But anyway, it's nice to be able to visualize the models and refine your axiomatization accordingly. Okay, so I just want to end now with a little theoretical exercise, and that's that we're going to show that transitive reflexive closure is not definable in predicate logic. So let's start with a new sheet. And to use that, we're going to use a nice tool in predicate logic called the Compactness Theorem. A nice mathematical result, a nice theorem. So we say that a set S of sentences is satisfiable in some predicate logic signature if there exists a structure that satisfies all the sentences in S. So if there exists a structure M for the signature such that for all sentences phi in S, the structure satisfies the sentences, those sentences phi. So basically, it's like saying the set of sentences has a model, some structure that satisfies all the sentences. And the compactness theorem says that a possibly infinite set of sentences, it's actually only interesting in the infinite case, so a set S of sentences is satisfiable if and only if, so IFF is if and only if, every finite subset of S. So it's only interesting if S is an infinite set of sentences, because otherwise S is a finite subset of itself. So the proof, well, it's actually very easy that if a set of sentences is satisfiable, it's trivial from the definition of satisfiability, then every subset of the set is satisfiable, not just every finite subset. So the left to right implication is easy. So the right to left implication is the interesting one. So we want to show that a finite subset of, we want to show that if every finite subset of S is satisfiable, then the set S is itself satisfiable. So to do that, we're going to prove by the contrapositive, we're going to suppose that S is not satisfiable. So what that means, well, we're going to suppose that S is not satisfiable, and we're going to show that then there exists a finite, so if S is not satisfiable, then it is not the case that every finite subset of S is satisfiable. So we're going to show there exists a finite subset that is also unsatisfiable. So suppose S is not satisfiable. Well, in that case, that means that we do not have a structure that satisfies all the sentences in S. So by the definition of validity, or rather of entailment, that means that S entails the sentence false. Because entailment says if we have a structure that satisfies all the sentences in S, then the structure satisfies what's on the right-hand side. But since we don't have any structure that satisfies all the sentences in S, then vacuously any such structure satisfies. We don't have any structures, so it's vacuously true that if we have any structure, it satisfies what's on the right, because there are no such structures. So then by the completeness theorem, that means we have a proof of false from the sentences in S. But that proof a proof is a finite syntactic thing. It's a finite sequence of formulas. And so the proof can only involve finitely many of the axioms of S. So we have some proof of bottom, but so consider a proof of falsity from axioms in S, and let S prime be the finite subset of S that are actually used as axioms in the proof. Only finitely many sentences from S can be used as axioms in the proof. So used as axioms in the proof. So then we have a proof of falsity from axioms in S prime, which is a finite set. So that means that S prime, that false is provable from S prime, which is a finite set. And now by soundness, so the soundness theorem we did last week, S prime, so false is entailed by S prime. And what this means, so this means for any structure that satisfies all the sentences in S prime, the structure satisfies false, but no structure satisfies false, so it means there are no structures that satisfy the finitely many sentences in S prime. In other words, S prime is not satisfiable. This says that S prime is not satisfiable. And that's as required, because we have shown that if S is not satisfiable, then there exists some finite subset such that S prime is not satisfiable. Okay, so a very nice result, and it's kind of non-trivial because this tricky right to left direction is far from obvious, in that if you just knew that every finite subset of a set of sentences is satisfiable, then okay, for any finite subset we can find a structure, but that gives us no obvious way of building a structure that satisfies all infinitely many sentences in general. So this is a rather important property of predicate logic, and in a sense it says that using this property we can learn something about limitations of the expressivity of predicate logic. So in particular we're now going to show so suppose we have a binary predicate R, we show that there is no first order formula or predicate logic formula, if you like, by xy defining R star, or let's do R plus, the transitive closure. So suppose there were then let's give ourselves two constants a and b. We consider the set of sentences firstly phi ab. So that should be just the end of a sentence. So suppose there were such a first, so here this is, suppose there were such a formula phi. So I'm going to consider the set of sentences. The first one says phi AB. So in other words, we're thinking that this is the formula expressing that A is reachable by a sequence of R steps, sorry, B is reachable by a sequence of R steps from A, where the sequence has length 1. And then we're going to add the sentence that actually, but it's nonetheless not true that R AB. And it's also not true that there exists a Z1 such that R AZ1 and R Z1B. And it's also not true that there exist Z1, Z2 such that R A Z1 and R Z1 Z2 and R Z2B. Let me just do one more, and it's also not true that there exist Z1, Z2, Z3 such that R A Z1 and R Z1 Z2 and R Z2 Z3 and R Z3B and so on. So it's an infinite set of sentences, and the point is this sentence says B is not reachable from A in one step. This sentence says B is not reachable from A in 2 steps. This sentence says B is not reachable from A in 3 steps. And this sentence says B is not reachable from A in 4 steps. And you can imagine how the sentences go. For each n, we have a sentence saying B is not reachable from n in n steps. And we've supposed that this formula says B is reachable from A in some finite number of steps. So then we see that if we take any finite subset of this set of sentences, it is satisfiable. So any finite subset of the above set of sentences satisfiable, because if we have some finite subset, then there's some number n such that we do not have the sentence that B is not reachable from A in n steps. And then we can find a model of all of this by simply defining a structure in which B is reachable from A in exactly n steps, and this is true, and all the other sentences will be true, and the one that's saying that B is reachable from A in n steps will not be there. So as long as we remove one axiom from this infinite set, then the set of sentences. If we remove any one axiom from the infinite set, any one sentence from the infinite set, then the set of sentences is satisfiable. So in particular, every finite subset is satisfiable, but the whole set is not satisfiable if phi really means transitive closure. And so if phi really defines the transitive closure of R. Because if it does, then this says B is reachable in some finite number of steps, but if we've got all infinitely many sentences here, every single one of them, then if B is reachable from A in some finite number of steps, there's going to be some sentence here, then that number of steps must be some n, and there will be some sentence here saying, but actually B is not reachable from A in n steps. So we've got the whole set of sentences is not satisfiable, but every finite subset is satisfiable, so that contradicts the compactness theorem. So this contradicts the compactness theorem. And of course, the compactness theorem is true. It's a theorem, so there must be some wrong assumption, and the only assumption we've made is that phi defines the transitive closure of R. So in conclusion, there can be no predicate logic formula defining the transitive closure of R. So since alloy does have the transitive closure, and transitive closure is a very useful is a very useful concept for expressing properties, sometimes one really needs to go beyond predicate logic, as the alloy analyzer does. Okay, so that's everything for this week. Next week we're going to change to an entirely different topic, which is something called temporal logic, which is about logic of time. But until then, there is a week's time, so let me say goodbye for now, and we shall be in communication again next week. So let's